Okay. Are we reporting to the cloud? Let's hope so. Okay. So last time what we discussed was this idea of using metric entropy to improve the rate for the empirical risk minimizers that work over a VC class. So the idea was using this Dudley's integral bound for the supremum of the sub-Gaussian process together with this estimate that we had of the VC dimension, if you recall. And so what we end up showing is, so this is like a generic result that we have that the excess risk of the ERM estimator is controlled by the Rademacher complexity of this, say, normalized loss function class plus a penalty, which is there because of the high probability nature of the bound. This part comes from the exponential tails in the bounded difference inequality, so that we are assuming the loss is one bounded. And so the point is to control this Rademacher complexity. We did a simple bound using Sauer-Shelah lemma that gave us like new root, new log n over n. You can do a better job. So you can translate that Sauer-Shelah to like an entropy or covering number bound, and then use the Dudley's integral to control that Rademacher complexity. And this gives you a root C nu over n, which is sort of optimal without further assumption or assumptions. And so the idea was to use this. Not sure if this is the right set of slides. Yeah, so the point was the Rademacher complexity is controlled by root nu over n. And so we define this sort of random process, which is scaled version of the empirical process, and then saw that this has sub-Gaussian increments in this empirical norm, let's say the metric defined by the empirical norm. And so if we can cover the set of functions in this metric, then you can use the Dudley's integral, and so that's what we did. So the supremum of this is controlled by the Dudley's integral, and this is, like, if you recall, it's just C over epsilon. Like, let's say 1 over epsilon to some constant times nu. So then you take the log, root nu comes out, and then the rest, sort of, you have to argue that this is a finite constant. Okay, so far so good. Any questions? Okay, so one thing that we are particularly interested in saying applying these results to is learning with half spaces. So if you look at this sort of hypothesis class or this function class that you're minimizing over, so if you recall, the ERMs or estimators, or is Hn, let's say argument H over a function class, right? 1 over n summation L of Hxi and Yi. And so, so we're restricting ourselves to the linear class. And for the linear class, we know that the VC dimension, let's say the loss is one bounded. I guess even if it's not bounded, the loss of VC dimension of the loss class will be bounded by the VC dimension of the H. And VC dimension of the H is bounded by D plus 1. And so this is further bounded by, let's say, 2D. And so if you plug in here, so this is like nu is proportional to D, so you get root D over n. plus root log 1 over delta over n. This is fine if d is much smaller than n, or d if it's fixed and then it goes to infinity. But if d is much larger, or if d is infinite, then we have a problem. Right? So we would like to learn that half spaces in high dimensions and also in infinite dimensions if possible. So somehow we want to get rid of this by adding more assumptions on the distribution. So maybe, can you maybe justify why going to higher dimensions might be more reasonable in practice? Anyone sort of has any idea? Okay, good. Yeah. So without talking about kernels, you can just maybe argue very simply that, let's say there are things that what you said is basically the essential idea. But let's say if I have points that are sort of in RD, but they're sort of like, this is one class, right? And this is the other class. Let me do something like this. Let's say this is a circle, like one is uniformly distributed and this circle centered at 1 on the x-axis, and the other one is just, say there is some sort of margin here. So the rest are sort of outside. So this is one class, the rest is, or it's like, maybe like this, the rest is sort of, so the data, one class is there, the other class is sort of inside here, right? What we can do is, so the equation for that circle, let's say, is x1 minus 1, let's say, squared plus x2 squared less than or equal to 1, or let's say less than or equal to r, right? And the other class is like x1 minus 1 squared plus x2 squared bigger than like r2, right? So there's some sort of radius r1 here, radius r2 here. So if I expand this, this would be like, let's say a x1 squared plus b x1 plus say x2 squared plus c less than or equal to 0, right? And the other one is similar, but for a different sort of c, let's say. So if you think of this, this is like a vector, you can say w star times x1, w star 1, w star 2, star 3, w star 4, times, let's say, 1, x1, x1 squared, x2 squared, less than or equal to 0, right? So that's the set of all 1, x1, x1, 2, x2, 2, such that this is like that. So if I define like this is like a phi of x, I can map my original vector, which is x1, x2, to this new space. So in this new space, the like one class is represented as, so if you like set, I don't know, what should we call this? So C is phi of x. And so this is like in R2. This is now in R4. So this is all QC is such that W star QC is less than or equal to, let's say, 0. The other one is QC, I don't know, bigger than or equal to like something else, like alpha. Right. So these classes are sort of linearly separable as you pointed out. So if you do go to higher dimension, there is a hyperplane. that can separate the two classes. And so you can add more and more, like all the polynomials of degree D, for example, you can sort of imagine you get complicated shapes. So if there's a polynomial of degree 10, for example, then you need to do like, you can count how many like coefficients you need for a polynomial of degree D in two variables. If it's like it's 3, then polynomial degree T, so it blows up. So the dimension of this becomes sometimes referred to as the feature map. It becomes very large, right? So that's a legitimate reason why you want to like do hyperplane, like learn hyperplanes in higher dimensions. So in higher dimensions, the data might be like linearly separable. That's in the case of classification. Okay, sounds good. So in order to improve this, I want to take a detour, talk a little bit about Rademacher complexity of this class and some other property of the Rademacher complexity, and then we get back to this problem. So this is like a detour that we'll take to answer that question. So the first thing that I want to look at is to figure out the Rademacher complexity of this linear class. So we have a bound via the VC dimension, which is like root D over n. And this is not good. I want to control this by assuming. So this is for W varying sort of arbitrarily. So I want to control this by. So W is fine. So the thing is that the X is sort of unbounded as well. So what I want to do is restrict the X, so X be bounded. Then I can sort of control the Rademacher complexity rather easily. So what we're going to do is like we're going to look at, I can always also absorb this B into X. So this we often do. So if you've seen like regression, you could define a new W by adding B to W, so you get a new vector and then 1x. So if you augment your features with a feature of 1 and then augment the weights by this intercept, so you get like W in inner product with X being X. So you can sort of simplify things a little bit. So we're going to look at this class, and I'm going to restrict W to a ball of radius 2. This in itself is not restrictive, right? But combined with the assumption that X is also bounded, this would restrict the class. So suppose I have vectors x1 up to xn. In a Hilbert space, for now, you can assume it just to be Euclidean space, RD. And then I'm going to assume that the xi's, the norm is bounded by rho. Okay, so xi's are in a ball of radius rho. Then the Rademacher complexity of this, let's say, this is, if you recall, the restriction. So H2OX is the set of all things that look like Hx1 up to Hxn as H varies in H2. This is controlled by rho over root n. And it doesn't have anything to do with the dimension anymore, right? So let's see how this works. So the definition of the Rademacher complexity is, so that's by definition of the Rademacher complexity. So it's the supremum over the inner product of a Rademacher vector with this vector. And in our case, this would be just the set of all things that can be written as Wx1 up to Wxn, where W is in B2. So B2 is the ball of radius. This notation is the set of all, let's say, W in the Hilbert space. Forget there, such that the L2 norm is bounded by 1. So let's say say RD. So if you recall, this is the definition of the Rademacher complexity of this, and then I can divide by 1 over n. I guess this 1 over n just comes out. So the first thing that we do is so can anyone justify this step? How do you get from this to this? Right, yeah, so the dual, basically this is just, I can write it as W summation epsilon I xi, and we are maximizing over B2. This gives me the dual norm of L2, which is just L2 again, right? So this is 2. Another way of saying it is just this is the Cauchy-Schwarz, right? The usual Cauchy-Schwarz. Okay, now I want to take the expectation over epsilon. There is like a simple trick that usually you can do. There's this next inequality. So why this is true? Expectation of that is bounded by the expectation of the squared 1/2. Jensen's inequality, yeah, this is basically the inequality that says the variance of something is positive. So if you square both sides. So by Jensen's inequality, so this is useful because I can now square things. So what I'm doing here now, define, let's say, let X be the matrix that has these rows, X1, X2. This is like the design matrix in statistics, right? So it's n by d, d could be infinite. And so X transpose would be, so it's like there's a bit of a overload of notation. So I'm viewing X as just as both a matrix and a set. So here it's a matrix. So you get X2, X1, X2, and then up to Xn. Right, and if I multiply this by epsilon, so this times epsilon is just epsilon1 up to epsilon n. When you multiply a matrix by a vector on this side, you effectively compute the linear combination of the columns, right, with these weights. So that quantity here can be written as X transpose epsilon. And then there is this trace trick. So this is X transpose epsilon squared, and I'm writing it like that. So why can we write it like this? Right, so the idea is like we do X transpose epsilon X squared. This is, let's say X transpose X transpose epsilon, right? So you get epsilon transpose, or let me do it the other way. This is equal to the trace. Why is this equal to the trace? Yeah, so this is scalar, it's the same as the trace, and now I can just circularly shift. So I'm going to move this to the front and keep the other one to the back, which is epsilon transpose X. Right, so this goes here. This piece goes there. With the transpose, I'm applying the transpose as well. So X transpose, epsilon transpose, it gives you epsilon transpose X. And so this is that. And then I want to compute the expectation, right? Expectation over epsilon of this, expectation over epsilon of this, which gives me what? So we want to calculate the expectation over epsilon of X transpose epsilon squared, which could give me the expectation over epsilon trace x transpose epsilon transpose x. So what can we do here? Online people can help as well. Interchange what? Right, we can do that. Okay. Okay, good. So x transpose comes out. X comes in as well. So we get this. So then what do we get? What is this? What? Right. So epsilon I and epsilon j's are independent. Like all the entries are independent. They're zero. I mean, this is basically the covariance matrix of the, and diagonal is just 1. Off diagonal is 0. So this is like this. So what I get is trace of x transpose x. And if you can have a look here, x transpose x is basically get x1 dot xn and x1 transpose dot x n transpose. This is nothing but trace of the summation. So x1 x transpose from 1 to n. Right, then I move trace inside. Trace of xi transpose, and this is just switch around, right? So trace of xi transpose xi, which is norm xi squared. Right, so what we get here is this is bounded by summation, right, from 1 to n, norm xi squared 1/2, and we're assuming each one is bounded by rho. The norm is bounded by rho, so this is bounded by root n rho squared, right? So just like equal to root n rho, right? And then I have a 1 over n here, so I get rho over root n, right? So the combination of the assumption on x and so this that bounding w alone is not problematic. When combined with this would reduce the complexity of the function class in a sense. Okay, that's one result that we want. So compared with like the thing that we had, like it was root d over n. This is great if this is bounded. And then the next one. Any questions? Questions? Okay. The next one is a form of a sort of contraction lemma for Rademacher complexities. So suppose I have these phi i's that are from R to R. They're 1 Lipschitz for simplicity. You can extend it to L Lipschitz. Just rescale everything. And then I'm going to define this, again, it's a bit of an overload of notation, phi OT to be the set. So I have a set T. This T here is T1 up to Tn. So I apply phi I to the ith element. Okay, phi 1 applied to T1, phi n applied to Tn. So as T varies in T, this carves out a new set. And the idea is that if the phi's are 1 Lipschitz, then the Rademacher complexity of this is bounded by the Rademacher complexity of T. Okay, so this is sort of called the contraction lemma for Rademacher averages. And it's very useful to peel off like Lipschitz functions. Okay, is the statement sort of clear? So it's very useful like dealing with loss classes because you get the composition, and if the loss is Lipschitz, you can just ignore basically the loss. So it's enough to show this for the case where all of these phi's are identity except the first one, because then I can recursively apply like this is going to be bounded like the one with everything is going to be bounded by the one that just peels off one, and then the rest the same, and then by symmetry, sort of like it doesn't matter which element this is on. So just convince yourself that it's good enough to just show it for the case, for this case. And then, so it's enough to, so this is the form of the Rademacher complexity. If I write this, the expectation, if I take the expectation over all the epsilons, the supremum is there, and then if I take the expectation over all epsilon, then that would be the Rademacher complexity. If I show this, and this is the Rademacher complexity on the other side, if I take the expectation over all epsilon. So if I just show this inequality when I take the expectation over epsilon 1, because epsilon, the rest of the epsilons are independent, I can then take the expectation over the rest, and this proves the inequality, right? So this is just enough. If I show this for any, basically for all epsilon i's from 2 to n, and all like, yeah, that's okay, just if I show this for all, let's say epsilon to epsilon n, let's say in -1 and 1 to n minus 1. So all possible like patterns here. We actually don't care actually. It holds for any real thing. So is this clear? So this is enough. So this notation here, I'm just taking the expectation with respect to this. These are fixed. The next step is to show that this is just enough to show this. It's just enough to show it for simplicity for a t which is in R2. You just replace this with some other thing. This t is not the same as the t above. So it's like, can anyone argue like why this next step is enough? So this t is not this t, but in order to not introduce extra notation, if I show something like this for any, basically, for any possible t, then that's good enough. Right, if you call this something like S, right, like epsilon i's are fixed, as this t varies in this t, t1 and s vary in some set, right? And so this is saying that basically the supremum of this is the same as the supremum of t and s in that set. So I'm just calling that t and s a new t, right? So just argue for yourself, it's not hard. If I'm not wrong, that this is enough. So this just simplifies the notation. If you don't like it, just go through with the argument like from here. But we reduce the problem to this. Now, what is the, say if I call it, so call this S, T1 and S varies in a new set, T prime, which we call again, rename T. So that gives you there. How do we proceed from here? Any idea? How can I show something like this? Online people can also. So epsilon 1 is a very simple random variable, right? So it takes values +1 and -1 and 12 e to 1/2. Phi 1 is 0. So my center has phi 1. So can you say that again?
So whenever you find that actually equals 5 1
It is, but 0 might not be in the set. It's fine.
Oh.
You can just have it like a center. You can center it around anything in the set. But why would that be helpful?
Well, I guess.
Positive or negative. So actually, like, I think you're on the right track, but the subtracting might not. I don't see why it would help. Right, but let's try. What is the basic thing that you can do here? So the basic thing is just to write down the expectation. Okay, it's just a simple. So we do like, it takes like two values with these probabilities, like soup. Let's say phi 1t plus 2 over t in t plus 1/2 soup negative phi 1 t1 plus t2. But that doesn't get any simpler than this, right? And then what I'm going to do is, any idea what next we can do? I want to sort of get, because phi is Lipschitz, I want to get deviations of phi like involved. I'm going to put a prime here. Doesn't change anything. Okay, now I can combine these. T and T prime and T. I get phi 1 T1 minus phi 1 T prime 1 plus T2 plus T prime 2. Okay. So now what is the next step? This is like phi 1 is Lipschitz, right? So this is going to be bounded by T1 minus T prime 1, right? But the trick is that I can just bound it by, but I can drop the absolute value and say T1 minus T prime 1 plus T2 plus T prime 2. Why can I drop the absolute value? Right. So because we're taking over both, so effectively we're just considering both the sign. So the largest one would be the absolute value. So I can do this. Now we like backtrack everything, right? So this is like separate the suprema. This would be basically this guy, right? Just take it out. Right? It's a very simple argument. So you see, the proof is simple, but it's an interesting idea. Okay. Questions? So I can peel off the Lipschitz functions out of the Rademacher complexity and combine with that linear thing. Then we're, yeah. Oh, this far? Can anyone else argue this far? So suppose I want to, let's say consider I have two simplicity. I want to argue that say Rademacher complexity of phi 1 T1 and phi 2 T2 as T1, T2, like T values in T. I'm going to say that this is bounded by the Rademacher complexity of the case where I peel both off. So I can just do once, right? So I can peel one of the off. I call this S, right? So this looks like what we proved is just shows that I can just drop this, the first one, right? Because as T2, like as this varies, this like it's like phi 1, T1, and S, right? Where T1 and S is in a new set. So you can apply that. Now I have this, I just peel off this again. Okay. Right. Questions? Okay. So we have the technical tools now. So let's go. I want to prove something in the context of classification, and we'll see some sort of more interesting sort of like leave the abstraction a little bit behind, see some concrete problems. So consider the classification problem where we have the labels are encoded as +1 and -1. X is in some subset of RD, could be like a Hilbert space later on. And I'm going to use this notation L01 for now to denote the 0-1 loss. Okay, so it's the expectation of this, if you recall, and this is just the probability. So this is like the probability of this classifying like a generic sample, like a generalization or X and Y are from the P. And I'm going to use this notation for a general affine function, right? H of W, B, and A. So we're going to first consider the linearly separable case in classification. So the classification problem. So it's some sort of assumption about this distribution, joint distribution. What it says is that if I draw a sample from this P, X, and Y, then there exists a W and there exists a B, like an intercept bias, such that this is the population classification loss is 0 for that hyperplane. So there exists a hyperplane that has 0 loss. Another way of saying this is just to expand it. There is a hyperplane such that at probability 1, Y is equal to H, W, B, and X, right? So every pair that you draw, X and Y, they're sort of, oh, sorry, should say sign here. This should be sign of this, right? So there's a hyperplane. So this is the estimate, look at the classifier. We classify according to the sign of this sort of affine function. So it tells you which side of the hyperplane it is. And so this is saying Y is equal to that, probability 1. Yeah, okay, yeah. So later on, we'll redefine the loss, but you're right. Yeah, this one as well. All right, sign that, right? So, okay, let me redefine this. We later on redefine things, but for this slide, just define the classifier to be this, then it's all right. And then it's also equivalent to saying that Y times this is bigger than 0, because saying that the sign matches, it's almost surely. Without loss of generality for some parts of the rest of the slides, I'm going to assume B equal to 0 by passing to this augmented feature map. So it just simplifies the arguments a little bit. So is this clear? Sort of, right? So that's like a picture. So you have the two classes, and then there's this hyperplane that separates the two. And in this case, there are multiple sort of hyperplanes. So anything sort of that's shifted a little bit. So actually, just let's say it's just everything is confined to this box. So I can just shift this a little bit, so things might not be unique, right? Depending on how the distribution is designed, or like how it is. So in this case, for example, I can have, assuming that this doesn't go on to infinity, this is another hyperplane, right, that works. Right? It need not be unique. And so in this separable case, let's say I get a sample size n, it's possible to actually compute a separating hyperplane. So if I have like a sample, this is like the population version, but I have a sample of size n, then this condition would be like, if I observe the training data, right, I from 1 to n, then I want to find, let's say, a hyperplane that has zero loss, and so let's say if I want to minimize, I can try to minimize actually the population loss by finding a hyperplane that, not the population, but the like empirical, basically. So the empirical loss would be I from 1 to n. Say yi. I'm going to assume the b is 0. Bigger than 0. It's like less than 0, sorry. So the loss would be, so this counts how many errors we have, right? We have a w, this counts how many of the sign matches. So this is equivalent to the empirical, I'm going to call it 0, 1 loss empirical for h, or hw if you want. Okay. So if I want to do the empirical risk minimizer, I have to find this minimizer over w. Equivalently, like I can just find the w. Okay. So the empirical like 0, 1 loss is just this. It's non-convex, but then things are separable. I actually can solve this non-convex problem. Any idea how to? So multiple ways actually, but you can actually find something for which this is 0, right? Which means that none of these like indicators are active. So basically we can, so in the separable case, we can find something like find w such that yi wxi is bigger than or equal to 0 for all I 1, 2, and right, so you can do like bigger than 0 if you want. If I can find some w such that this holds, then the 0, 1, like empirical 0, 1 loss would be 0, and I can't do better. So that would be the solution. There might be multiple solutions, but this is a set of linear equations, right? So this is sort of an LP feasibility problem. So you can just like minimize the cost function 0 subject to this. I mean, it's just a linear program. There are multiple ways of doing it. And so it can be done in polynomial time. A non-separable case, in general, finding the minimizer of the 0, 1 loss is NP hard. But for the separable case, you can actually find this. The thing is that there might be multiple solutions. Generally, there are many solutions. So the question is that, is there something like, because for the training, it's like the case where you overfit, essentially. It's not overfitting, but there are multiple solutions that make the loss be 0. That can give you the 0 loss. The question is that which one does better for future data. right? That's the point. So what do you guess? Like, what might be like best to do? Sorry. Okay. Great. Yeah. So like an intuitive thing is like something that just separates them barely. This is so this also works, but the one that like the dashed line seems better because sort of there's this margin, which is like the minimum distance of all these points to the line. This is much higher than this. So you can imagine that like the distribution, like next sample might be a little bit here, I pay a price, but if I perturb, like there's a perturbation going on, then if I have like a large margin, I still like have 0 L1. So it's a very intuitive idea. So this one has a smaller margin. The data says you can imagine this would be a harder problem because I can try to find the maximum margin separating hyperplane, but in this problem, let's say for the so actually if the actual distribution is confined to this, both of them are fine. But the thing is, in practice, it might not be. So like some of these I might not have seen, right? So this like there might be some like the actual margin might be like the population margin might be smaller than this. So I'm going to pay a price, but this is the natural idea. So if I want to, if there are multiple solutions, I'm going to try to find the maximum margin separating hyperplane. And hopefully that has a good generalization performance. So to find the margin, I have to sort of figure out what the distance of points are to the hyperplane. And so if you have a point X, you want to compute the distance. This is like an interesting math problem. And it turns out, as an exercise, you can do it, that if you have a point X, and this is the hyperplane, then the distance would be like the absolute value that's divided by norm W. And you can see, like, if I rescale W and B, the hyperplane doesn't change. And the same goes here. Right? So if I rescale this by alpha and alpha and alpha here. So for simplicity, I'm going to assume that W is like norm 1, because this is like there's a scale invariance. Then we can require that the points to have a distance at least gamma to the hyperplane. So there is this hyperplane. SD minus 1 is this set, right? So it's just the sphere, sort of all W in RD, such that norm W is 1. So I'm gonna assume that there exists W in B such that W is norm 1, and this is so you can see that this is, so if this is like positive, and this is also positive, so basically this is the absolute value here, right? So to the side of the, so for these guys, let's say that W transpose X plus B is negative, but the like Y is also negative. For these, it's positive, and the Y is positive. So basically, Y times this divided by this is the distance of all the points. And so this is with W equal to 1. This is saying that this is being bigger than 0 is separability. This is being bigger than gamma means there is a margin of gamma, right? So that's how you can impose this condition. One issue is, so imagine like again, B is 0, I absorb everything into X. B is 0, if I rescale X, or in this case, if I rescale X and B, I can change the margin. So it's not well defined. There's some sort of a scale issue. So one way is to like fix the scale of X as well. So we get this definition. So distribution P on RD times, like this is X, let's say times Y, is separable with gamma rho margin if there is a W star on the sphere, and B star in R, such that if I draw a random pair here, they have this margin condition, and the size of X is bounded by rho. Okay, so I'm restricting the size of X. So this makes it a little, like, gets rid of the scale issue to some extent. So this holds almost surely. So that's the assumption that you put on P, which is a strong assumption. But you can extend this to the empirical version. So when you draw a sample of size n, so you can just replace the empirical distribution here. That will give you the definition of the margin. And if you have an empirical distribution and things are separable, you always have a margin. Right? So there is some sort of positive margin. The thing is that this is at the population level, it makes sense because for like a finite set, you can always if things are separable, you can make it small enough such that that happens, assuming that there's no ties basically among the classes. But then in the population, it's a very strong condition. It says that no matter how many points you get, there is a positive gap. Everything is clear, right? Okay, so that's that. So how do I compute the maximum margin classifier? So again, I'm going back to the general definition with W. So this is the distance of, so we are now having a training data here. This is the distance of sample I from the hyperplane, Fourier transpose X plus B. Defined by sort of, yeah, yes. And so this is the minimum distance, so this is the margin, right? It's the minimum distance of any point to that. And so I'm now maximizing the margin. Okay, so that's the max margin classifier, and this is called Hard-margin or hard SVM, support vector machine. So this looks like a difficult problem to solve, but you can actually reformulate it a little bit. So what I'm doing here is like a trick that you can do. So what I'm doing is, so I'm rewriting this problem like that. So introduce a slack variable of alpha, and instead of maximizing this, I'm going to maximize over WB and alpha. So I'm claiming that this problem is equivalent to the above problem. So can anyone maybe justify why the two problems are equivalent? Yeah, so this first thing to observe is this is equivalent to minimum yi w transpose xi plus b is bigger than or equal to alpha. Okay, then what? Equality holds for optimum alpha. Right, so another way of saying it, I guess you guys are pointing to it, I'm just going to first optimize over alpha. I'm going to maximize over alpha first. When you maximize over alpha, you have to push it until you hit this, because you can see it's like linear in alpha. To fix W, if I maximize over alpha, I have to just linearly goes up, it's like monotone in alpha. So the best is like pushing alpha to this. So the optimal alpha would be like the minimum. and then the rest is just maximize the minimum. Right? So this is like a trick that you can do. And this problem now, you can see that the problem is like there's a scale ambiguity. So if I rescale B and W and alpha together, right? So like multiply W by a factor, C and B. So if I change like, so W alpha WB, if I change it to C alpha, CW, CB, then it cancels from the like objective, the C cancels out from the objective, the C also cancels out from the these. So I can just like fix one of them to be like, I can fix alpha to be something that I want. Right? By doing this, I can just say fix alpha to be 1. It's the same problem. So then we reduce to this simpler form. You just don't need to optimize over alpha anymore. And that's what is called the hard-margin SVM. It's a convex problem, right? So you minimize the norm subject to, so it's like a quadratic problem, convex problem, and it's easily solvable. There are many methods to solve this. Okay. And questions? So the reason why I introduced the B back here is because you can see this version of the hard SVM, it doesn't regularize the B. So if I just absorb the B into X, W would contain the intercept and you would regularize with it. It doesn't matter in practice as much, but for simplicity of the following discussion, you're just going to assume that B is absorbed there. But just note the subtlety that in practice, you don't usually regularize B for theoretical like arguments. It's just simpler to just not carry around the B anymore. So you're going to analyze this simplified version, the hard-margin SVM, and just point out that a more general version would be like, this is basically minimizing W subject to yi h. So whatever function that you have, h of xi bigger than or equal to 1, h happens to be in this case W x, but you can like imagine later on that this is basically really the form. So you have a parametric form of h, and then you're minimizing over, sorry, some sort of a norm of h. That's the problem. Some sort of a norm. Yeah, let's forget about this for now. You have to define what the norm is, but yeah, let me not mention this. This is, come back to this later. So we have this result that if you have a gamma rho separable distribution, and if h hat n is the hard margin classifier, so you can see I removed the sign. I'm going to redefine the L01 to apply to like real valued functions. Then the this classifier, the L0 norm is bounded by this, and you can see the instead of the d here that you're used to pay, you're now paying rho over gamma squared. So if rho and gamma are fixed, then this just goes down like 1 over root n, independent of the dimension. Okay. And in fact, what we're going to show is we're going to show this with this replaced by a bigger loss, like the ramp loss, which gives you a stronger result, an upper bound on the L01 loss. Let me introduce in the redefining the notation, which helps us a little bit instead of like carrying the sign. So I used to have like the sign here. H hat n could be like the sign of this. I'm redefining it to just be this linear function. Instead, we change the definition of the loss instead of, so that's like the L0 loss that we used to have. It's defined on binary input. But now I'm gonna just redefine both h and the loss. So L01 of h and y would be just this. Okay. For the classification, this is equivalent, but this is just takes any like real valued output, and depending on the sign of it, just y times this being less than 0 means the signs do not match. It is like an extension of the L01 loss. But this is useful because then I can relax it. This might have more information, right? Just beyond the sign. So if we like redefine the loss and redefine the functions now, like we're looking at linear functions, the loss is like this. So this makes sense. And then I can relax then to other loss functions like L of phi. I'm going to replace this 1 less than 0 with some phi here, right? And then we can like define the corresponding like generalization loss to the expectation of this, where when y and x are from the distribution P. Okay, does this make sense? Okay, so if you look at this, the phi that corresponds to the 0, 1 loss is basically this guy. So that's the 0, 1 loss. The phi for 0, 1 loss is just indicator t less than 0. Right? If t is less than 0, so this is phi of basically t equal indicator t less than 0. So this is applied to like y hx. You can call it the margin if you want. There's the hinge loss, which is an upper bound. This red thing is the hinge loss. I can use that. You can see this is an upper bound on the 0, 1 loss. This is the 0, 1 loss. So hinge loss is an upper bound, which is convex and also Lipschitz. One Lipschitz. Ramp loss is this one that we have, which the ramp loss just goes like, okay. Just goes like follows this, and then here just continuously goes down. Right? So that's an also upper bound, but it's not convex, but it's one Lipschitz. Okay, so the ramp loss is bounded and Lipschitz. The other one is unbounded, like but convex and Lipschitz. Okay. Both are upper bounds on L0 and 1. So the hinge loss is like maximum of 0 and 1 minus t. Right? So this line is 1 minus t. And then when you hit 0, you take that, and then ramp loss is just minimum of 1 and the hinge loss, right? So you follow the hinge loss until you hit 1, and then you cap it at 1. So that those are like the functions. Sounds good. So what I'm going to prove now is the equivalent of this for the ramp loss, and the ramp loss bounds the L0, and there's no sort of the population version, like there's like L0 hn minus the best population function, which is 0. For the best population one, there's like there's a function that makes it 0. So it's like this is also the excess risk, if you want, over that class. Okay, so let's try to start proving this and then we'll continue next time. So by assumption, there exists a W star such that for all I from 1 to n, the W star is in the sphere such that we have this margin condition, right? So both of them are part of the assumption. And then if I define the class of linear functions such that W is in 1 over gamma times B2, just the rescaled version of the ball of unit radius. By the definition of the hard margin classifier, I have this inequality. So anyone can argue why this is. So W hat n is the solution of like the weight vector of the hard margin classifier. and W star is the one that satisfies those inequalities. That's the hard margin classifier. So we put it there. W hat n is argmin W subject to yi Wxi is bigger than or equal to 1 for all I. Yeah. What has this fewer? Yeah, so this is the population version, like there's. So if you imagine dividing both sides of this by gamma, right, you get yi W star over gamma xi bigger than or equal to 1. So W star divided by gamma I is feasible. And so this is saying that for all the feasible W's, this is the one that minimizes W. Right, so then the norm of this has to be less than, right? This is like an optimality. So this is optimal. This is feasible. So I get that. So with that, then the hard margin SVM belongs to this function class. Right? It's the W hat and it's like this. So we are minimizing over essentially let's say not minimizing, but just the hard margin like SVM belongs to that class. And then yeah, one more point and then we'll stop next time. Continue. Let L and Ln be the population empirical ramp losses. Then I would like to argue also that Ln of h hat n is 0. So why is this 0? That's the population ramp loss. So ramp loss looks like this. It goes down. At 1, it's 0. And at 0, just 1. So L ramp. So this is applied to so this Ln h would be basically 1 over n summation I from 1 to n L ramp h x I and yi, which is just 1 over n phi ramp yi h xi, and in our case it's just going to be, so for this guy it's just going to be 1 over n summation I from 1 to n phi ramp yi w hat n and xi. Okay, so that's the thing is, for any solutions of this problem, these are all bigger than 1, right? Bigger than or equal to 1, and so the ramp loss is 0 here. Right, so the empirical ramp loss of the weight vector of the hard margin classifier is 0. So then what I'm going to do next time is, this is the L is the population ramp loss of this, will be equal to the population loss of this minus the empirical loss, and then I'm going to bound this by the supremum and then use the empirical process theory to control this. Right? Just maybe for the next time, go through this. Just convince yourself that this inequality, this is true. So, but basically, any solution of this minimizes, like for the L0, empirical L0 is 0, and also like the ramp loss is 0 as well. And then we're done. Okay, not done, but we'll continue next time. Okay, sounds good. Okay, thank you guys. See you next time.